Chapter 4, Part 6. We're to our last portion of Chapter 4, and we're going to be putting together all of our lovely calculations. So before we jump to something new, I want us to review the unit factors we have learned since Chapter 3. So the unit factors that help us with very specific calculations in chemistry. So the ones dealing with moles. So our first one was 1 mole is equal to Avogadro's number, which is 6.022 times 10 to the 23rd things, and we use this unit factor when we are counting the number of atoms or molecules. We used that in Chapter 3, and it hasn't really followed us much into Chapter 4. It will show up at later points. It just hasn't right now. Our second unit factor we learned in Chapter 3 was 1 mole is equal to the molar mass, which we don't have one specific number that always goes here, in grams. That number that goes in the molar mass spot comes from adding together all the average atomic masses from the periodic table, the number with all the decimal places, for a molecule. So this unit factor is different for each chemical, but it's always 1 mole equals this different number in grams. Okay. The third unit factor from Chapter 3 was the mole ratio, which I don't even have any more detailed thing to write, but I'm going to say this comes from a balanced chemical equation. This is when we compare one chemical formula to another chemical formula using the coefficients, the whole numbers in front of the chemicals in the balanced equation, to make this mole ratio. Some number moles of some compound equals some number moles of another compound, where the number comes from the coefficient and the compound comes from the chemicals in the balanced equations that we are looking at. So those came from Chapter 3. So in Chapter 4, we are adding a new unit factor. So the last video we learned about molarity. So molarity itself is a unit factor. It's a complex unit. It is defined as moles of solute divided by liters of solution. Okay, so if we have the molarity, which is different for every solution because molarity is measuring the concentration, how strong, how much solute, how much stuff is dissolved in a solution, that it becomes a unit factor for that one specific solution. Again, it's moles of solute divided by liters of solution. So for my molarity, to write it as a unit factor, just like the mole ratio and just like the molar mass, it's not always the same number. So I'm going to write the number sign. So whatever the molarity is, so if it's a 0.75 molarity, then it'll be 0.75. We'll go in that number spot. Moles of solute, where solute is just the chemical, is equal to 1 liter of solution. That is our new unit factor. We can use a molarity to convert from moles to liters or liters to moles. So this is a unit factor. Okay, we used it that way in the last video, but what we're going to do in this video is put it together where molarity shows up along with some of these other unit factors, more specifically when it shows up along with the mole ratio. That's the one we did not practice in the last video. So we're just going to come up with some examples of when, or how these calculations would show up. So our textbook, which loves its little flowcharts, here are flowcharts on how to convert from, if you're given grams of one chemical, chemical A, and you're supposed to get to grams of another chemical, chemical B. Well, we've actually learned how to do this. This is just mapping out the molar mass, stoichiometric coefficients, which means mole ratio, and then the molar mass. But what we added, so that was shaped like a U in Chapter 3. There's a picture that looks just like that from Chapter 3. So what we just added was this part. Molarity or volume are things that we can solve for as well. So you would start maybe with grams of the chemical, and it would ask for the volume of chemical B. And so this flowchart gets you there. I'm still not a big fan of this flowchart. Instead, I like to use units and unit factors to cancel out until I get what I'm looking for. So that's how I'm going to approach these. Before we get to the calculations, titration is the technique, the lab technique that we use when, like, for all the calculations we're going to be doing with this. So titration is a technique used to determine the molarity of a solution. So it's already been made, but we don't know its molarity. Or it's already been made and we know what its molarity is sort of, but we need to know it very accurately. We will do a titration. So in this titration, you will fill the burette, which is a container that measures how much liquid has been let out of the bottom. So the liquid comes out the bottom down there. and the markings on the side measure how much has been released. So we put a solution there, so we're easily able to measure how much solution we put into this flask at the bottom. Well, before I would start draining the burette, I would first accurately measure the amount of other chemical that I would put down here. In this picture, they used a pipette because the other chemical, so chemical A versus chemical B, chemical A happens to be a solution, so they used a pipette to measure it out. If chemical A was a solid, we would use a balance and a solid and weigh paper to measure out it and put it in there. And so what we can do is we can know the amount of chemical A. We can also know the amount of chemical B. And based on that information, we're able to solve for, well, one thing we could solve for would be the molarity of chemical B. We could potentially solve for the molarity of chemical A, whatever. But what happens is we mix these chemicals together until we get to the end point, which is when, in the case of this class anyway, we have an acid-base indicator. It's a chemical that changes color to tell us when the solution is at the end point, which is when you should end the titration. The end point is when the balanced chemical equation, the mole ratio equivalents, are accurate at that point. So basically it's when both reactants are the limiting reactant. So both reactants are gone. So you see a color change when this happens. Okay, so the problems that we're going to do, the calculations we're going to be working on, are coming from someone who did this procedure and then got their data. Okay, so that's what's going to happen. So let's try one. So let's read the question. How many grams of sodium hydroxide are needed to neutralize, there's a hint that it's a neutralization reaction, 20.0 milliliters of a 0.150 capital M, which stands for molarity, H2SO4. Now, we could just start thinking, okay, what am I solving for? What am I starting with? Before we jump to that point, don't I have two different chemicals? NaOH and H2SO4. Whenever I have two different chemicals, I need a balanced chemical equation between them because I need how are they related to each other? Well, this time it didn't give us the balanced chemical equation. It also didn't give us the molar mass, which I will give us here in a second. But step number one is going to be to write the balanced equation. So how many grams of NaOH, so I have NaOH, are needed to neutralize 20 milliliters of 0.150 molarity H2SO4. So these two are going to mix together. Now, I have states of matter. I can check the solubility rules. That is aqueous. This is an acid, so as far as we're concerned, it's always aqueous. It didn't tell us the products. So we're going to have to use what we have learned about our metathesis or neutralization reactions, which occur just like metathesis reactions, where we need to identify our four ions and take the positive ion here and pair it with the negative, and then the other two go together. So I'm going to take sodium ion, which I know is a +1 charge, and the sulfate polyatomic ion, which was a -2 charge. When I put those together, I'll have Na2SO4. I can check my solubility rules. That is aqueous. Then I'm going to take hydrogen ion and hydroxide ion, so hydrogen ion, hydroxide ion, and put them together, and that makes HOH, which I'm going to write H2O. And unless we're told otherwise, H2O is going to be a liquid. So let's look at our equation and check to see if we're finished. Is it balanced? Well, we look at this. 1 sodium, 2 sodiums. Crap, not balanced. Okay, so I'm going to put a 2 right there. Well, I have 2 sodiums. I have 1 sulfate, 1 sulfate. It says 2 hydrogens and 1 oxygen. Well, the other way to think of this is it might be easier to think of this as HOH as you balance. So when you do that, you think of like it's a hydrogen and a hydroxide. Well, right now I have 2 hydroxides at the beginning and 2 hydrogens, but on the product side I just have 1. So I'm going to add a 2 right there. And then my equation should be balanced. So now that I have my balanced chemical equation, it's feasible for me to start looking at the calculation. I didn't know how these chemicals were related. I had to figure out how sodium hydroxide and sulfuric acid were together in order to do this. One way to help me, because there are lots of numbers in this question, right? So one thing you can do to help yourself is kind of just keep track of, like, to rewrite the problem, I guess. So how many grams of NaOH? Well, we are solving for grams of NaOH. And if it would help if you write, like, I don't know how many grams of this chemical there are. And we need to know how much would react with 20.0 milliliters of a 0.150 molarity H2SO4. So if it helps to write those numbers underneath H2SO4, that will help you remember what goes where. Now I've got to do a stoichiometry calculation. So I'm going to have to, we're solving for grams of NaOH. We need to start with a number. We were given two numbers, 20.0 milliliters and 0.150 molarity. We can only start with one of them. Well, we never start with a unit factor. And if you recall, the first slide of this video, I wrote down 4 unit factors, and one of those unit factors was molarity, which means we never start our calculation with a molarity. So I'm going to start my calculation with the other number, 20.0 milliliters of H2SO4. And I'm just going to get myself ready to do calculations. So I know step 1 is going to be to cancel out milliliters. Well, right now, I don't see any unit factors at all. So what I'm going to do is I'm going to take my molarity and rewrite this the way that I recognize. So 0.150 molarity means 0.150 moles of H2SO4 is equal to 1 liter of the H2SO4 solution. So that's a unit factor. I can't use that one yet, though, because that says liters and this says milliliters. So I'm going to use my metric prefix because I don't have any other information here. Okay. So at this point, my calculation would be in liters. So I'm going to use that unit factor, 1 liter for every 0.150 moles of H2SO4. So this molarity is only a useful unit factor in this specific problem because we were told that molarity in this problem. So what I'm telling you is 0.150 is not always the number that goes in front of moles. H2SO4 is not always the chemical. This and this change based on the information you were given. You get the number part from right there, you get the chemical part from right there. Okay. So I just converted milliliters of H2SO4 into moles of H2SO4. Wonderful. We need to get to grams of NaOH. That's not even the same chemical. So I know in my next step, whatever I do, I have to cancel out moles of H2SO4. So thinking of my unit factor, if I get to I could use molar mass and go from moles to grams, but I don't really care about the grams of H2SO4. I don't care about atoms or molecules, so I'm gonna go ahead and set myself up with the mole ratio. So to do my mole ratio, I have to come back here and look. Well, what's in front of the H2SO4? Well, I don't see anything. That implies it's a 1. Sorry, my dogs are barking. What's in front of the NaOH? Well, a 2. So at this point I have moles of NaOH, but it wants me to solve for grams. Well, I'm going to use the molar mass. So the molar mass I forgot to write down in the calculation, so I'm just going to tell you. It is 39.99711 grams. So at this point I have grams of NaOH, and I need to solve for grams of NaOH. I didn't plan my space well. I'm going to do equals sig figs. 3 sig figs, an infinite number of sig figs, 3 sig figs, an infinite number of sig figs, 1, 2, 3, 4, 5, 6, 7. Looks like my answer should have 3 significant figures because it's the smallest number of the options. So when I use my calculator and round to 3 sig figs, I get 0.240 grams of NaOH. In this problem, what was different? Was this step. Otherwise, we've done questions like this in chapter 3. Okay. And in that step, we've done actually questions using molarity as a unit factor in the last video as well. Okay, so let's do some more. So here's another one. How many liters of 0.500 capital M, so molarity of hydrochloric acid, are needed to react completely with 0.100 moles of lead 2 nitrate, forming a precipitate of lead 2 chloride? It mentions a bunch of different chemicals in here, and we do not have a balanced equation, so I'm going to start there. So I need to read this question and figure out how to set this up. So how many liters of hydrochloric acid are needed to react completely with 0.1 moles of lead 2 nitrate? So that's going to tell me that hydrochloric acid is going to react with lead 2 nitrate. And then it says forming, so arrow, a precipitate of lead 2 chloride. Well, if we look at this, is this going to be the entire equation? I don't see any hydrogens or nitrates on the other side. And to obey the law of conservation of mass, we have to have the same number of atoms on both sides. And right now I have 0 hydrogens and 0 nitrates. So if you recognize this, well, lead and chloride came together. Oh, this is just a metathesis reaction. So hydrogen and nitrate are the two ions not represented yet. So they're going to have to come together. When I put them together, +1, -1, that's supposed to be a 3. I have problems with 3s. Man, just with this pen. Okay, so balanced equation. We've got to look to, or equation, we've got to look to see if it's balanced. 2 nitrates, 1 nitrate. Oh, crap. So I'm going to put a 2 right there. My hydrogens and my chlorines are both unbalanced. I'm going to put a 2 right there. So, okay. Now I want to go back and let's look at the question and start thinking about numbers. So how many liters, we're solving for liters, of HCl are needed to react completely with 0.100 moles of lead 2 nitrate? So what I need are liters of this. What I know is I have 0.100 moles of this chemical. I also know this chemical is 0.500 capital M molarity. So I have two numbers. I need to start with one of them. So what do you think? Start with the moles or start with the molarity? Well, not the molarity. We always start with the not molarity. So I'm going to write 0.100 moles of PbNO3, so lead 2 nitrate. And I know I need to cancel out moles of lead 2 nitrate because that's what I started with. So I'm going to go through my list of unit factors. Do I care how many atoms or molecules? No. Do I care how many grams of lead 2 nitrate? No. Do I care how lead 2 nitrate compares to another chemical? That would be like the mole ratio. And actually, yeah, because I need to get it into HCl. So, HCl. The only other unit factor we had on our list is the molarity. Did we have a molarity of PbNO3? And the answer to that is no. I do have a molarity, but it's of HCl, so I didn't have that unit factor. I'm going to put a 1 right here and a 2 right there, coming from those numbers. That unit will cancel. I have moles of HCl. I know moles of HCl are going to go on the bottom to cancel it. So I go through my unit factors. Do I care how many molecules of HCl? No. Do I care how many grams of HCl? No. Do I care how HCl compares to another chemical? No, because I need HCl. So that leaves me with molarity. Well, we do have a molarity of HCl. 0.500 molarity. So 0.500 moles of HCl is equal to 1 liter. So 0.500 moles to 1 liter. That lets me cancel out that. I'm going to grab my calculator, do 0.100 times 2 divided by 0.500. Look at significant figures. It looks like 3 significant figures is what I'm going to have. My calculator says 0.4, but does that have 3 sig figs? Nope. So I'm going to do this, adding 2 zeros to make it have 3 significant figures. Okay, we have 2 more examples. Okay. We're once again in the situation where I do not have a balanced equation. Thankfully, this is a chemical reaction that we actually have already written the balanced equation for. The first problem we did in this video was 2NaOH aqueous plus H2SO4 aqueous, arrow Na2SO4 aqueous plus 2 H2O liquid. Okay, so we could have recognized I needed that because I have 2 different chemicals and I need a balanced equation for them. And I was lazy. I stole it from earlier, but it's a neutralization reaction that is also a metathesis reaction. So now it's time to read the question and figure out what we're solving for. Well, it says, what is the molarity of an NaOH solution if 48.0 milliliters of NaOH is needed to neutralize 35.0 milliliters of 0.144 molarity H2SO4. When you first read this and you look at the numbers, well, we got 3 numbers, so you're like, crap. Most people's first thought, honestly, is that this will fit nicely in the M1V1 equals M2V2 equation, which we talked about as the dilution equation in the last video. But here's my question. The dilution equation, it only works for one chemical. Like when I'm taking one chemical and making a solution of that same chemical. Do I only have one chemical in this problem? I have 2 chemicals, which guarantees I need the mole ratio, and there is no mole ratio in the dilution equation. So the dilution equation is not the way to go here. If you do M1V1 equals M2V2 because you're like, Beth, you're an idiot, I can do it. you're going to get the wrong answer. So you go ahead and try it, and then we'll go through this, and then we'll see how this goes. So I'm going to treat this like another stoichiometry type of problem. So we're solving for the molarity of NaOH, so I don't know the molarity of this. We do know that there's 48.0 milliliters. We know the molarity of H2SO4 is 0.144, and we know there are 35.0 milliliters. Okay, so what we're solving for? Well, the molarity of NaOH. So I'm going to break that down and write moles of NaOH divided by liters of NaOH, or what I'm solving for. Okay, now then we got to pick something to start with. Well, there are three numbers. Those three numbers, well, one of them is a molarity, so I will not be starting with 0.144 molarity H2SO4. We never start with a molarity. Our answer needs to have a unit on top and a unit on the bottom. So honestly, when I start, I need to have a number on top and a number on bottom, because my answer needs to have two units, so I have to make sure there's two units. Well, the bottom number needs to be the liters of NaOH. So we look at this. We don't directly have the liters of NaOH, but I have the milliliters of NaOH. Doesn't that get me really close to liters of NaOH? So I'm going to put that on the bottom because that's almost what I need. So on the top, just process of elimination, it's going to be 35.0 milliliters of H2SO4. So what I'm going to do right now is I'm going to ignore the 48.0 milliliters of H2SO4. You can't see this. I'm crossing it out with my finger. That doesn't help you at all. I'm ignoring, I don't want to cross it out, so I'm ignoring this right now. Okay, so pretend like he's invisible. What we're going to focus on is try to get milliliters of H2SO4 into moles of NaOH. Well, unit factor-wise, for milliliters, all I know is there's 1,000 milliliters in 1 liter. So I'm going to start there. Now I have 1 liter of H2SO4, and I need to convert it into something. Well, I could go back into milliliters, but that's not helpful. Of the 4 unit factors, the only one that has liters in it is molarity. And that says some number of moles of some chemical is equal to 1 liter. Well, we're going to be looking at this. So that some number is 0.144 moles of that some chemical, which is going to be H2SO4, would convert this into moles of H2SO4, which is awesome, but it's not quite what I want. I have moles of H2SO4, I need moles of NaOH. So I'm going to convert using the unit factor mole ratio. So 2 in front of the NaOH, 1 in front of the H2SO4. So if I stopped right now, the only units that are not crossed out are moles of NaOH on top, which is good, and milliliters of NaOH on the bottom, which isn't quite good because I need it to be liters. I normally wouldn't erase this, but I'm running out of space. My last step needs to convert the milliliters into liters. So now I would grab my calculator, take 35 divided by 35.0 divided by 48.0 divided by 1,000 times 0.144 times 2 times 1,000. Looking at my significant figures, my answer needs to have 3 significant figures. So what I ended up with when I did my math, rounded to 3 sig figs, is 0.210 molarity of NaOH. If you did M1V1 equals M2V2, you would not have gotten this. If you did M1V1 equals M2V2 and then did some sort of in your head mole ratio, I guess you would have gotten this, but I really hope that you understand what you did, because this is going to be a really common type of problem, not just in lecture, but also in lab. So, one more. This one, what I want you to do, read the question. I've already given you the balanced equation. It might look gross. Don't be freaked out by the balanced equation. It's just a net ionic equation. There just were not very many spectator ions. Okay, so here's the balanced equation. I want you to read the question, and I want you to try this. The information that I'm going to give you is that the molar mass of Fe, and this could be Fe2 plus, is 55.845 grams per mole. With that information and the balanced equation and the information, I want you to hit pause, try this problem. When you're finished, hit play, and we'll go through it together. So hit your pause and practice this one. Okay, so hopefully you did. So when we are solving this, we're supposed to solve for grams of iron. Okay, and what we know, I kind of didn't use my space well here, is we have 47.20 milliliters of this permanganate, and that it is a 0.2240 molarity. And we want to know how many grams of iron there are. Now, there are other chemicals here, but notice the only two chemicals I care about are the permanganate, MnO4-, and iron. Okay, so I go to start my calculation. Well, we were given two numbers, one of them a milliliters, one of them a molarity. We are going to start with the milliliters because we never start with the molarity. The molarity is always going to be a unit factor. So I have milliliters. I'm going to start by going to liters. Once I have liters, I know that liters need to be on the bottom down here. I'm going to use molarity as this unit factor. So 0.02240 moles of MnO4-, which came from right there. So now I know I need to cancel out moles of permanganate, because that's the unit I need to cancel. So at this point, the mole ratio is the most useful unit factor. So in front of permanganate, there's a 1. In front of iron, there's a 5. And then my last step is to go from moles to grams. 55.845 grams. Cancel, cancel. Unit factors, it looks like I have 4 for my answer. So I got 0.2952 grams of iron. Okay, cool. Hopefully that went well. We used molarity, mole ratio, and molar mass in that equation. Now, we actually have one more part of this same question. Same question, so we're going to actually need to keep that 0.2952 grams of iron here. But the top part's exactly the same, so this didn't change at all. The bottom part says, if the sample, so because I guess I didn't read it out loud, but what happened was that iron, the Fe2+ that we just calculated, came from the sample they dug up in the ground that's made up of iron ore. If it's iron ore, that means there's other crap in there too. So what we just calculated was in that chunk, there's 0.2952 grams of iron. The rest of it was crap. So what they're saying here is the sample had a total mass of 0.8890 grams. So that's not of iron, that's just of the rock they pulled out of the ground. We're supposed to calculate what is the percentage of iron in the sample. So thinking about this, this is not a fancy stoichiometry type of calculation. This is a percentage. So percentages. If you got 17 out of 23 on a quiz, how could you figure out your percentage on that quiz? You take your points, 17, divided by the total points, 23, times 100. So if we want to calculate the percentage of iron in the sample, we're going to take how much iron was there divided by the total times 100. So how much iron? Well, I'm taking my answer from the last question. How much was the sample? Well, we were told 0.8890 times 100. Grab my calculator, go to 3 sig figs, 0.3321% iron. So you might see some things like this that show up that seem like they're not things we've talked about. But things like percentage calculations, it's kind of assumed that you're feeling good about this, okay? That you understand percentages. So these types of problems, not just this last one, but using molarity as a unit vector, they're not going away, my friends. Even with labs later in the semester, after we finish chapter 4, this is not going away. So my very strong suggestion for you is if you're having problems, come talk to me about it. Ask questions, send me a message, whatever. Let's get this straightened out. If you're feeling good, then awesome. This is the end of chapter 4, which I know is a huge chapter, but good job surviving.